Yeah, now for something completely different. George, why are you recording too?
Alright, speak
Oh,
loudly.
no, Michigan. I mean, you can take videos of us if you want. Take a video of Misha. Take a video of Misha. That's what we do. Alright. Dynamic time warping is our subject of presentation today. And it is an algorithm. Believe it or not. Unfortunately, Mr. Paul has unfortunately, Mr. Paul has not graced us with his appearance. So instead of giving the normal presentation, we control for all 45 minutes of this class. By Elliot, Kinzel, Nove, Kim, Chesapeake, and Vitz Park. And also Davy Whitman. All right. Okay, all right, any questions? No,
Is this understandable?
No. Not yet.
Noah,
Elliot.
our slides aren't in the right order.
Ah.
It's like someone has dynamically warped time. Back to the presentation.
All right. All right, there we go. So we'll start off with our question. What is Noah saying? This is actually a pretty common question, and no one knows the answer.
Here we see Noah, as pictured here, performing a lovely waveform for us, and we have to try to identify what that waveform really is. But luckily, we have some sample waveforms. Also, things that Noah already said, like one of these waveforms. And each of those has a characteristic waveform. So we have to try to match it up with the waveform that it's closest to. But there is an issue. Okay. And the way we do that is dynamic time warping.
Alright, so Noah Singer shared with us yesterday for the whole class his wonderful presentation that took us all the way back to 3-sat and problem difficulty. But we thought, well, why stop there? So the Big Bang occurred 13.8 billion years ago and created billions of stars and galaxies in the first trillionth of a second. This continued for a while. After that, Earth and our solar system formed 4.5 billion years ago. The Earth formed again, the Earth reforms, and this process went on for a little while. Some of the first Earth occurred, sort of showed up around 3 to 3.5 billion years ago, and it had evolved by the 2.7 billion mark. And then humans showed up, 2.5 billion years ago. So George Boole was born in 1815, a little while after that. And he worked on DQ, algebraic logic, Boolean algebra, and then Turing showed up in 1912 and he made the Turing machine, which Noah so nicely talks about. And then Noah Singer took us through everything between then and modern computing. So now that we're there, why don't we go ahead and talk about our algorithm. What is he doing?
For the next cool slide. I
Okay.
printed out some quotes.
So, the general gist of the algorithm is that on each of our waveforms, we have to match a point from one waveform to the other. And it will match every point of both waveforms to a different point. We have to minimize the total length of these mappings. We'll describe why this works later. So to do that, what we do is we form a graph between the distances between the 2 points and a path transversely that is the smallest length using diagnosis. So how do we form this one? So here are our two waveforms. This is the Noah sample waveform, which is the waveform we're trying to identify. And here's waveform that hints of someone saying, I am literally the greatest. Now, we've offset them by a small difference, but in our descriptions, it will only be by 0.25. So the difference between these two places is 0.25.
And that's just for reference. That's not an actual meaningful value. It's just so you can differentiate the two when we actually display it.
So what we've done is we've labeled the distance from the bottom point in the sample to all of the points in the comparing form and left it on the graph. And now we do that for the next point, the second point, which is this one, and we so continue until we have the entire table filled out. Now we can form. Now we have the issue of actually choosing the mappings. So if we the mappings take place as a collection of points on this table. For instance, this point is the mapping between the fourth on the sample and the second on the pair, which would be here and here. So if that is included in our set of mappings, then we would have this point in our graph that goes through here. Now, because of some constraints that we'll discuss in further detail later, we can actually say that, like, at every point, the only other points that can get only other mappings possible are effectively these 3 points that are like to the top and to the right there. And those are the only ones that you can actually map to. So if we represent these mappings in a graph that contains all of the set, so we map the first 2 points here, and then keep going, form a graph of the optimal mapping. The way we use Dijkstra's on this is that the weight of each line is equal to effectively the size of the node that is the sun that's going to go to. So we form here a graph that shows the optimal mappings between these two waveforms.
Right, it's like the shortest path through the graph of differences, which is like sort of you kind of have to see the not even see the implementation, but like understand that what you're looking for here is this like set of points that moves in a relatively uniform order, so as to like encompass the entire graph, but also is like the minimum of the distance between the points, so they like sort of match up. Misha?
Your initial points, like you have 2 sets of points, right? 10 of each. How do you choose them? Arbitrarily, or they're like specific requirements?
Iterate through every single point. That's and then
wait, every single
the
point.
initial points, you mean like this one?
Oh, yeah.
Or what do you mean?
No.
Or
So like,
He's saying how
oh, so like you can't really do this for like a continuous function, right? This is
No, it's
only for discrete data.
Right.
All right, got you.
Okay, so to actually like represent why this function is interesting, why it's called time warping, I've taken the same mappings on the other side and shown them as if the 2 graphs are stretched out. Here's the sample form of what Noah is saying, and here's what he's comparing to. So for these 2 points, the mapping on this graph shown here is directly on the diagonal, and it's straight up. There is no time difference between them. Now, once we get to this hump, over at the top, the hump is shifted over. It's later in time. And since we're trying to find how close the waveforms are in their similarities of the shape, not necessarily like how long they are, how far spread apart they are, this algorithm recognizes that difference and can map them together. And this mapping makes a diagonal line, since the time is different. You can see that when it actually goes above the diagonal to the left. And then again, once it goes to this, since it's shifted backwards in time, it's warped backwards. It goes below the diagonal on the characteristic graph. So, like, this represents how much time is being warped forward or backwards. So, it's going for more forwards in time here and then backwards in time there. And actual time warping is sadly unrelated to our project.
Yeah. So now we're gonna check for understanding.
Okay. I think a good way to do this is if we go back to the slide of all of the sample possible waveforms. Understanding that this algorithm is shifting time backwards and forwards to find the one that has the most similar waveforms in the thing. Which of these waveforms looks like it would be the most similar to what Noah's saying?
Can you flip back real quick? Yeah, I'm actually the greatest.
Yeah.
Right.
I don't know. You guys should run the algorithm.
Wait, so what do you wait for that one? Are you saying this one's most similar?
No, you take the first capital is this possible to understand. It's like outline.
No, that's not the point. It's not. Is it possible to actually the greatest? It's one of the other.
These are the only three possible things that I've seen. That's like the basic overview of the algorithm. Now, now we're going to talk in more detail about the constraints that we actually apply to the algorithm.
Okay, so constraints basically make it faster to see if the check points do that, or they like give you like a general idea of what the solution should look like. So, alright, yeah, you guys have to like pay like, close attention because they're gonna be checks for understanding later. So the first constraint is monotonized. I don't know how to say that, but so basically your path can't go backwards in time. Basically, when you're constructing like when you're going through Dijkstra's, you can't go like you can't have a negative slope basically. Like you can't go downwards. Yeah. And then it ensures that you don't like repeat any features in your alignment. And next is continuity. Basically, you can't like skip any points, and every point has to be mapped to another point. Yeah, we have boundary conditions so that you start at the left bottom corner, and you end at the top right corner, and that basically makes sure that the alignment only like doesn't only consider partially like one of the sequences. And the warping window is just that a good path is supposed to stay like close to like the straight diagonal, so it basically gives us fewer points to check because with this constraint we like check fewer points. And the slope constraint, it's like you don't want to go too fast or too slowly. So yeah, it's just like this is bad, that's bad. Alright.
Yeah. So like, you guys sort of understand the difference between our like constraints that actually define how we compare paths and how we can sort of optimize it by just cutting out like the sort of peripheral cases that most likely won't be visited.
Yeah.
And you mean that, Andrew?
P and Q like given.
You can implement them, yeah, but it's not like something that's inherent to like based on.
David.
So this you wouldn't be able to use this to like find like if a certain audio clip was in a video or something, like you have to like search through like.
Yeah, like the idea is that you see if one audio clip is similar to another, you can't like pick out waveforms unless you have like sort of isolated what you're looking at.
Yeah.
How does length do going back and after? You have two very close space points that are both better before and after.
What?
Like,
Wait.
why do you need to have that constraint?
No, but how does that constraint do what your S thing does? So you're claiming that you can't keep that not.
Right.
You have just two that don't go back.
Can you just have
No. Like, the issue is, with the backwards in time thing, is that this one waveform, it's like it's not a function, I guess. This one waveform is being mapped at this, is being mapped in multiple places.
So for example, why can't you just move the red first bit like a little bit?
I mean, it would still be like going back in time.
Okay, that's right.
That's like faking it till you make it, you know? That's not good.
Thank you, Josh.
Okay, so this is a real thing. You guys have to name this.
Wait.
What is R for if you go back like 3 slides? What is R?
That is like the area within you are actually looking for like,
Radius.
viable paths.
How did you get it?
It's something you supply, so you can
Okay.
sort of just say like, just stop looking at things that are past that.
Sorry?
So like going back to David's question, if you like ignore the boundary constraint condition, then you would be able to like pick out audio clips, right? You know, there's
You could pick it out of a single audio file that only had something similar in it, right? But like what I interpreted his question to be was like, can you take a sort of like bunch of sounds in one audio clip and like distinguish one single sound out of this? And the answer is no for that one, but more likely yes for your question. Yeah, so just to clarify.
Wait, Josh, you're gonna
Yeah,
check
they were
what you're
supposed
saying?
to name them.
Wait, hold up.
That's the check for understanding.
I got a question. So, length of the file doesn't matter, right? Like,
What?
the length of the audio file in this case doesn't matter, right?
No.
All right.
Because you're comparing every single one.
But like the position in the audio file does matter, right? So it's like if you had like an hour-long audio file and like a recording of Sarah saying "wow" one time, and like one was positioned like 3 minutes and one was positioned 53 minutes in, right? Like a random sound that's located closer to the "wow" would match better than the "wow" at 3 minutes.
That's if you implement like the starting position and the new position. Do you feel?
Yeah.
Because it's like if you.
But if you don't do that,
If you don't do that, it'll just find wherever it's happiest.
all right. But you usually don't do that because like you're not using this to check.
Right. It,
Cases
it
like that.
depends on your like application.
All right.
Josh.
Yeah. Hey, Haran, name this.
Answer to.
Pretty close.
Okay.
You can't go back in time. That's the moral of this story.
Oh yeah, that was like the actual.
No, you just gotta give what the reason behind this.
Well, actually, it was.
Do it.
Sport.
Nice. Good job, Ron.
I'm gonna clap it up for Haran.
Yeah, hold on. Let's just go back for a second and appreciate Ron's contribution. Okay. Somebody else. Want to explain this one, Sam?
You cannot go too far away from.
Right. That sort of cuts down runtime.
Oh, is that what would like limit what Misha was saying, where if you have an hour-long thing? Is that the
No, what
reason?
Misha was saying is that like, if you try to match a stream like a short clip to like a ton of stuff, you won't find what you're looking for unless you remove the constraint that says the first clip has to start at the beginning of the first clip of the second clip and the end of the end of the second clip. This is like any graphing in general. Yeah. Now we can talk about our actual performance.
You talk about cherry machines
We actually did that already. Noah Singer explained it for us.
first. Okay.
We just had to give an intro to Noah Singer's lesson.
I'm actually the greatest.
There we go. Okay, so it's a 2D graph. Can't really get around that. So it's n-squared, unless, I mean, you can shorten it by cutting off the edges, but it's n-squared at the end of the day.
Even Dexter's doesn't sound better.
But like, the algorithm itself has to formulate that like graph in the first place.
Oh, okay.
So it's upper bounded. Yeah. Never mind his right side.
Like,
Yeah. Obviously, optimization. No, but yeah, as we explained.
Where did you take this from?
Someone made a good presentation.
Not us.
Oh, hey guys, no, I have a quote. I have a quote to read to you guys. It's not yo. Okay. This is from Elbert Hubbard. Do not take life too seriously. You will never get out of it alive. Pretty smart. Yeah. Alright guys, this is from Helen Keller. She says, keep your face to the sunshine and you cannot see a shadow. That's genius. Blind. Okay guys, Albert Einstein quote here, right? You can't blame gravity for falling in love.
Okay, so what we're doing now is Josh is stalling. Noah has time enough to build this presentation, which he like made in JavaScript.
Noah, you need some stalling?
you want to calm down?
Dude, I got you.
Joseph.
Piranha, eat you. Alright, this is from not
Hey, John, you got any more quotes?
Yeah, I do actually.
Wait.
What up?
But there's
Oh
presentation.
yeah, we got.
Here is Noah's waveform.
No, is this written in abstract tension?
No! Please. I'm putting that like down. So this is our first graph, and I can't exactly remember what it was Noah was saying. And it's gone ahead and generated both the graph, the comparison waveform, and the optimal paths for comparing the two. So, yeah, of course. No, please.
Is this actually possible to understand?
Well, let's see how similar that was to what he originally said.
I'm actually the greatest.
Oh, hold on.
Wait, Noah, what does the D mean?
So the D is the distance of the graph, which is a valid way to just compare how similar different patterns are to what your original waveform. Yeah. So
Is that like the sum? The sum?
This is
Yeah, some of the patterns.
this is him saying how possible is this to understand.
Right. So if you can see similar points like this sort of max, they get mapped to the similar highest points in the corresponding curve. But we have our last waveform, which is indeed the most similar. What was it? Oh, was it? Well, Noah Singer was in fact saying, "I'm literally the greatest."
No, wait, this one. This
Yeah,
is not that
yeah,
one.
it was.
I'm pretty sure it's this one.
Really?
Just let me use the example.
We have
You
actually.
can see right how the same shape waveform has all of the points mapped.
And you can also see that this has the shortest distance of path compared to the other two.
Okay.
This is available online, believe it or not. Don't look at it, you'll crash.
Yes, Misha.
So can you name any actual applications that use this?
We're working on it.
That is the.
I mean, like,
That's one of them.
That's one of them. Sure. Like,
Dude, where's the minutes?
So here's our garbage implementation in Java that I wrote 20 minutes before the first presentation. But it actually works. I just didn't do the Dijkstra's part because that's a huge hassle.
we also didn't do that, so we can't do it.
Right. So that implementation is not on this presentation, sorry. But yeah, so we start off with our n-squared array, and then we just iterate through all the points and use some function of the difference between 2 points, which I just defined to be the absolute value of the difference between the y values.
We should also say how in case you forgot Dijkstra's, the actual algorithm doesn't vet. It goes through all the nodes for that first and labels each one with the minimum distance to get to it. So we do that for all of the nodes until we get to the last node. And then it starts to
Right. And then this is something that it would spit out if you bounded it with r equals 3. So you have a window of 3 on each side of the center bound. So as the path lengths increase, or as you go further down the graph, you see it start to diverge in specific points where the 2 points, or where the 2 plots were sort of different. So here's our source code. Yeah, this is for the JavaScript implementation. And if you copy and paste this into an HTML file, it actually does work. So you can go to noahbqm.com/dtw2.html, and that's just this. Well, DTW is the implementation that you can actually read. Well, it's right there. Just look at it.
Oh yeah.
Why did you?
I did minify it. How do you think it got this crap?
Oh, I used to read like right?
No, because obviously, how else would we understand it?
What's missing between you like that?
Because it was bad at minifying. Okay, I didn't write it. So now we can talk about. Okay. Yeah. So audio analysis, you can use it to compare results of data mining. And you can do correlation power analysis.
It's pretty much unused for audio. Here's another
I didn't see this slide. So is everyone sort of on board with what we sort of outlined about this algorithm and how you use it, like what it just means in general? Are we just like, are we all here?
Can we linger on this?
No.
We should linger on this. What?
That's okay. I'm okay with it. We cannot play the video, it's not school appropriate. Yeah.
Any? Oh wait.
Your resources. So we actually lied. Here's what Noah Singer was actually saying. Oops. I lost it.
Okay, any questions?
No.
Whoops. Okay. Thank you. Any questions?
Yeah, let's.
Wait,
I want to hear it.
Go back one more.
Wow.
Josh, go back one more.
Yeah, but it's like mapped to the video.
Wait, we gotta play the analysis.
Oh, there it is. There it is. There it is.
There.
You got it. The video audio is off. All right.
Oh well.
Go back, go back.
Ah.
Oh wow.
Wow.
There it is.
Okay.
Josh.
I would.
All right.
This joint's broken.
Any questions?
All right.
Thank you, Josh.
That's the wrong number.
Wrong live device.
Okay.
Oh wait, no, don't take a picture of that.
Okay. Any questions? Stop. Stop. Give me that.
All right. Thank you, Noah.
Oh, Mr. Paul, he's one last quote. Martin Luther King Jr. In the end, we will remember not the words of our enemies, but the silence of our friends. Happy Memorial Day. Happy Memorial Day.
Now here's 3 questions.
Question number 1. Josh, how many more posts do you have?
I have like maybe 2 or 3. Oh!
Read all of them.
Float like a butterfly, sting like a bee.
Come on, you got 10 minutes to kill. You can ask questions about. You can ask questions about the presentation.
Actually, we can go back to more detail for all of the certified stressors.
No,
I suppose.
I think I have to censor the video.
Okay. Wait, what?